In Chapter 14, we're going to talk about the properties of liquids. Now, all of the properties that liquids have depend on one thing, and that is something called intermolecular forces. Basically, these are just the forces of attraction that exist between molecules. Without intermolecular forces, there would be no such thing as liquid water. These forces hold the molecules of water together. Without these forces, DNA could not exist as a double helix. The molecule would simply unravel. In fact, without intermolecular forces, life as we know it could not exist. So what is the nature of these intermolecular forces? Well, first, let's consider ionic compounds. What is it that holds the ions together in ionic compounds? Why do ions stick together? It's simply because they have opposite charges. For example, in salt, a sodium ion is attracted to a chloride ion because they have opposite charges. This is a representation of a crystal of sodium chloride. The purple represents the sodium ions, the green represent the chloride ions, and all of these ions simply stick together because the opposite charges attract one another. Now, do molecules stick together? Well, of course they have to, because if they didn't stick together, for example, as we mentioned earlier, water could not exist as a liquid. The only reason liquid water exists is that all those water molecules are attracting one another. Sugar could not exist as a solid if the molecules of sugar were not attracted to each other. So without those intermolecular forces, there would actually be no liquids or solids. Everything would be a gas. But why do molecules stick together? Well, it's the same reason that ions stick together, because opposites attract. It's pretty obvious why ions attract one another. When two atoms come together and form an ionic compound, one atom ends up positive and the other negative, and so obviously the two are going to attract one another. But what about molecules? How can molecules have positive and negative charges? When two nonmetals come together and form a covalent bond, they're sharing electrons. One atom is not taking the electrons from the other, and so they're not forming a positive and negative ion. So what is it that allows molecules to have positive and negative charges? The answer is a property known as electronegativity. Whenever two atoms form a covalent bond, they both actually want electrons. They would both love to take those electrons, but they can't because the other atom is unwilling to give them up. So they have to share, but it doesn't mean they're going to share equally. Electronegativity is basically a measure of how strongly atoms attract electrons. So whenever there's a covalent bond between two atoms, both of those atoms are pulling on the electrons. We can gauge the electronegativity of elements by simply looking at their location on the periodic table. As you go down the table, electronegativity decreases. Therefore, of course, as you go up, it increases. As you go across the periodic table, electronegativity increases. So the most electronegative element on the periodic table turns out to be fluorine. It's the farthest to the right and the farthest to the top if we ignore the noble gases. And of course, we do ignore the noble gases because they don't want electrons at all. They have no interest in getting electrons. And of course, the least electronegative element would be in the opposite corner. Francium is the farthest to the left and the farthest to the bottom, making it the least electronegative element. Now let's take a look at some molecules. The hydrogen molecule consists of two atoms of hydrogen. Each one contributes one electron to form a covalent bond. So initially, each hydrogen atom owns one electron. When they form the covalent bond, they each contribute one electron to that bond, and so essentially they now own half of a pair of electrons. Well, from an electron standpoint, whether you are the sole owner of one electron or the half owner of a pair of electrons, it comes out mathematically to be the same. And so the hydrogen molecule is neutral. It has no positive or negative charges. The hydrogen went from one proton and one electron to start with, and it has one proton and half a pair, or one electron, to end with. The same is true with the fluorine molecule. Each fluorine contributed one electron to a bond, so the fluorine atoms went from being the sole owner of one of those electrons to the half owner of a pair of electrons. And so the fluorine molecule, like the hydrogen molecule, is balanced and it's neutral. Now, what happens when two atoms are not the same? The fluorine atom is, of course, much more electronegative than hydrogen because fluorine is the most electronegative element on the periodic table. So hydrogen and fluorine don't share equally. The fluorine is pulling the electrons toward it, so the fluorine is getting the lion's share of the electrons. Perhaps the fluorine now has 2/3 of the pair, and hydrogen has only 1/3. That means that hydrogen is missing a bit of electron, and therefore that gives the hydrogen a partial positive charge. And the fluorine, because it's getting the lion's share of electrons, has a partial negative charge. This Greek letter delta represents partial. So anytime you see delta plus or delta minus, that simply means that it's a fraction of a charge. Now, as an analogy, let's consider the sun and a cloud. So we'll imagine that the sun represents the proton in the nucleus of the hydrogen atom, and the cloud is that electron. In a hydrogen atom by itself, that electron is completely covering the proton, and so you don't feel the positive charge because it's being blocked by the electrons, just like we don't feel the sunlight because it's being blocked by the cloud. Now, suppose the cloud begins to move away from the sun. It slowly begins to expose part of the sun. So now we don't feel the entire intensity of the sun, but we just feel part of it. Sort of the same kind of thing that happens with our hydrogen fluoride molecule. As the cloud of electrons is pulled off of the hydrogen atom, that positive nucleus, or that proton, begins to peek through, and we begin to feel part of its positive charge. Because the hydrogen fluoride molecule has a positive and negative charge, we say that it has what's called a permanent dipole. Dipole simply means two poles. So just like a battery has a positive and a negative pole, the hydrogen fluoride molecule also has a positive and negative pole, and permanent simply means that it's always present. We can also refer to hydrogen fluoride as a polar molecule. A polar molecule is simply a molecule which has poles. So a hydrogen fluoride has a positive and negative pole. It is a polar molecule. And then finally, the reason, of course, that hydrogen fluoride molecules attract one another is because of these poles. The negative fluorine end of one molecule is attracted to the positive hydrogen end of another molecule, and so all of these hydrogen fluoride molecules can link together. And that's the nature of the intermolecular forces in these polar covalent molecules. Now, what about molecules that only contain one element? Molecules like that, of course, are going to have to share equally. For example, in the hydrogen molecule, as we've said previously, because the two hydrogen atoms have the same electronegativity, the cloud of electrons will remain equally distributed around the molecule, and the hydrogen molecules have no charges. There is no positive or negative pole. So we refer to molecules like this as nonpolar molecules because they don't have a positive or a negative pole. So here's a fact for you. all intermolecular forces are due to positive and negative charges in molecules. So the only way that two molecules can attract each other is they have to have a positive and negative pole. So here's a question for you. Do nonpolar molecules attract each other? Well, we've just said that the only way molecules can attract each other is to have positive and negative charges. And we've already said that nonpolar molecules don't have those. So will they attract each other? And the answer is absolutely. And you're thinking, now wait a minute, that seems like you just contradicted yourself. But the fact is, it's pretty obvious that nonpolar molecules must attract each other. For example, if you look on the periodic table, most of the elements on the table are solids, yet each individual element consists of only one kind of atom, which means they're not polar, yet somehow they're sticking together. If you take something like nitrogen, which is a gas, you've probably heard of liquid nitrogen before. They use it to take warts off and such. They use it to cool magnets. And the only way to get liquid nitrogen is you lower the temperature until the molecules stick together and form a liquid. If nitrogen molecules, which are nonpolar, didn't attract each other, it would be impossible to turn it into a liquid. But the fact is, all substances, if you lower their temperature far enough, they will form liquids. And that proves beyond all doubt that those substances must somehow have attractions for one another. So let's see if we can figure out how we can address this apparent dichotomy here. How can molecules that apparently don't have poles attract each other when the rule is they have to have poles to attract each other? As an analogy, let's take a look at the Indianapolis Motor Speedway. That's where they run the Indy 500 road race. It's a 2.5-mile track, and the track is perfectly symmetrical. So each half of the track is exactly the same as the other half of the track. So logically, how much of the race would a particular car spend on the right side of the track compared to the left side? Well, since the track is symmetrical, we would expect it would take the car just the same amount of time to go around the right side as it did the left, and each individual car should spend half their time on each side of the track. Sort of like the electrons in a hydrogen molecule. They spend half their time on one side of the molecule and half on the other, which is why it's balanced. However, if you looked at the track from the air, suppose we went up in the Goodyear blimp and we took a photograph of the track at some point in the race, would you expect to see half the cars on one side and half the cars on the other? Very unlikely. More likely, you would see probably a bunch of cars, piled up on one side of the track and a few stragglers or the leaders on the other side. If you took another picture a few minutes later, you might find the opposite. Now there's a bunch of cars on the right and not very many on the left. If you took 1,000 pictures during the course of the race, and in each picture you counted the cars on the left and on the right, and you added them all together, you'd find that it came out equal, that the cars spent half their time on one side and half on the other. But for any instant in time, if you froze the action in a particular instant, you would find that it's not balanced, that there's more cars on one side than the other. The same thing can happen in molecules. Normally, we would expect in a hydrogen molecule to find the electrons equally distributed around the molecule. So half of them are on the right and half are on the left. But because the electrons are sort of randomly flying around in the molecule, it's possible that for a moment we might find the electrons on one side of the molecule rather than the other. Now, for this particular instant in time, the electrons have moved to one side, and now this end of the molecule has more electrons, and it makes this end of the molecule negatively charged, and the other is positively charged. So nonpolar molecules have what's known as a temporary dipole. Most of the time, the hydrogen molecule is nonpolar because the electrons are equally distributed. But at some time, we'll find the electrons are off balance here. The electrons have moved more to the one side than the other, and for that moment or that instant, the molecule will be polar, but it'll only be polar temporarily. So nonpolar molecules only have positive and negative charges some of the time rather than all of the time. So in general, a molecule with a temporary dipole will not have as strong of intermolecular forces as a molecule with a permanent dipole. So what determines the strength of the intermolecular forces in a molecule? It depends on what kind of molecule you have. In a polar molecule, it's the difference in electronegativity. In a polar molecule, it's like a tug of war between two atoms over the electrons. And the greater the difference in the strength of the two atoms, the more the electrons will be pulled and the larger that permanent dipole will be. So, which would have a stronger dipole then, HCl or HBr? Well, chlorine is higher in group 17 than bromine, which means chlorine has a greater electronegativity than bromine. So the difference between hydrogen and chlorine will be larger, and we would expect it to have a stronger dipole. So the answer, of course, would be the HCl. What about nonpolar molecules? In the case of nonpolar molecules, electronegativity is unimportant. In a nonpolar molecule, it's a tug of war between two equally matched opponents. If it's a hydrogen molecule, each hydrogen is equally strong. If it's a fluorine molecule, each fluorine atom is equally strong. So in nonpolar molecules, it's the number of electrons in the molecule. You may remember when we were speaking about this a few minutes ago, what makes a nonpolar molecule have its temporary dipole is the random motion of the electrons from one side of the molecule to the other. So the more electrons that are moving back and forth, the greater that temporary dipole will be. So let's compare propane and decane. Propane, with 3 carbons and 8 hydrogen atoms, has a total of 26 electrons in the molecule. C10H22 has 82 electrons in the molecule. And our rule is whichever molecule has the greater number of electrons should have the greater temporary dipole. And so decane will have stronger bonds than propane. And it's pretty obvious if you looked at the two substances, because propane is a gas at room temperature and decane is a liquid. The reason decane is a liquid is because there are stronger bonds between the molecules holding them more tightly together. So, in summary then, for polar molecules, it's the difference in electronegativity that we care about. In nonpolar molecules, electronegativity is a non-issue. All we really care about in that case is how many electrons are in the molecule. So, which one is stronger, the permanent dipole in a polar molecule or the temporary dipole in a nonpolar molecule? The answer is, it depends. There is no one single answer for that question. So what we need to know is, what does it depend on? What is determining which of these two will be stronger? Well, for polar molecules, they are normally stronger than nonpolar molecules, and that's logical because a polar molecule has a positive and negative end all the time, and a nonpolar molecule has it only part of the time. So when I say all other things equal, if a polar and a nonpolar molecule have the same number of electrons, they would be equal in terms of their temporary dipole. So the only thing that would be different is that electronegativity difference that makes a permanent dipole. So, for example, let's compare methane and water. Each of these have 10 electrons. And so they're equal in that point. Methane, however, is a nonpolar molecule. It's a tetrahedron, but water is a bent molecule, which means it's going to have a permanent dipole. An easy way to compare the strength of their intermolecular forces is to look at their boiling points. The higher the boiling point, the stronger the bonds must be, because in order to boil a liquid, you have to break the bonds that are holding those molecules together. So methane boils at a very low temperature, minus 164 degrees Celsius. So it's very easy to boil methane because its intermolecular forces are pretty weak. Water, of course, boils at 100 degrees Celsius. That's 264 degrees higher, which tells us the bonds in water must be substantially stronger than the bonds in the methane. So in this case, polar definitely beats nonpolar. Now let's take a look at a second example, oil versus water. Oil is very much like methane. It's simply a long chain of carbon atoms with hydrogen atoms attached to it. It's also a very nonpolar substance. However, oil won't even boil. You can heat oil as hot as you want. Eventually it might catch on fire, but you can heat oil well above the boiling point of water and it will just sit there. It's not going to boil. That's why if you've ever noticed, if you put a piece of meat into a skillet with hot oil and it begins to splatter, that splattering is not the oil, it's the water boiling when it hits the hot oil. So because oil has a much higher boiling point than water, that means that oil has stronger intermolecular forces. So even though oil does not have a permanent dipole, because oil molecules have a lot of electrons, it's got a very strong temporary dipole. So temporary can beat permanent if the temporary dipole is large enough, meaning if that molecule has a lot more electrons than the molecule with the permanent dipole. One thing you will need to be able to do is to identify whether a molecule is polar or nonpolar. Now this may seem to be a daunting task because there are millions of molecules out there, and I can give you any one of those millions on a quiz or exam and expect you to tell me whether it's polar or nonpolar. Luckily, there is a fairly easy way to do this. If you think back to our chapter on acids and bases, there are thousands of acids, and I told you that you would have to be able to identify whether an acid was strong or weak, and what made that easy is there were very few strong acids. Only 6 of them. Almost all the acids were weak, so you only had to memorize a very small list. Well, the same thing is true with polar and nonpolar molecules. Most molecules are polar, so all we have to do is just learn those few instances when a molecule will be nonpolar. So there's a few basic rules that you can follow. Our first rule, which is pretty obvious, is if there's only one element in a molecule, it has to be nonpolar. The only way a molecule becomes polar is if there's unequal sharing between the atoms in the bond, and with the being the same element, they have to share equally. So things like O2, P4, S8, those are all nonpolar molecules. It doesn't really matter what the molecule looks like. 8 sulfurs, they all have to share equally. The 4 phosphorus atoms have to share equally. So that's a simple one. Now, the more complicated one is when there are 2 elements, because when there's 2 elements in a molecule, it can go either way, polar or nonpolar. So it comes down to the shape of the molecule. If you remember back to chapter 12, when you have 2 elements in a molecule, it's possible that they can be in a straight line or they can be bent. So if 2 elements are in a straight line, if it's a linear arrangement, like carbon dioxide, then that molecule will be nonpolar, because the 2 oxygens, even though they're stronger than the carbon, they are pulling against each other and they're canceling each other out. So carbon dioxide is a nonpolar molecule. And not surprisingly, carbon dioxide is also a gas. Gases, by their nature, have weaker attractions. Rule number 3 is if you have two elements in a trigonal planar arrangement. So a trigonal planar molecule would be something like sulfur trioxide. In the case of sulfur trioxide, the three oxygens, even though they're stronger than the sulfur, they are essentially pulling against each other and they're canceling one another out. So if you have two elements and it's a trigonal planar arrangement, it will also be nonpolar. And again, not surprisingly, sulfur trioxide is a gas. Our next rule is if you have two elements in a tetrahedral arrangement. So something like carbon tetrafluoride. The four fluorines in this tetrahedron are much stronger than the carbon, but they are equally spaced around the center, which means the four fluorines are fighting against one another and they are canceling one another out. So this molecule is also nonpolar. It also happens to be a gas. So let's summarize briefly the material we just finished covering. First of all, if there's only one element in a molecule, then that molecule will always be nonpolar. So those are the easy ones. Similarly straightforward, if there are three or more elements in a molecule, it will always be polar. So really the only ones that we have to give a lot of thought to are molecules that contain exactly two different types of elements. If there are two elements in a molecule, it can go either way. It might be polar, it might be nonpolar. As we saw a few minutes ago, it depends on the shape of the molecule. So to have two elements in a molecule and for it to be nonpolar, all of the atoms have to be in balance with each other, which means the molecule has to be very symmetrical. So for two elements, that occurs in three cases, as we just saw, if the molecule is linear, or trigonal planar, or tetrahedral. Those are the three very symmetrical geometries of the molecules. In those cases, the molecules will be nonpolar. Otherwise, the molecules will be polar. Now, hydrogen bonding is a special type of permanent dipole. We separate it from your regular permanent dipoles because it's much stronger. Hydrogen bonding is simply a very powerful permanent dipole, and as you can probably guess, it contains hydrogen, but not just hydrogen. There's essentially three instances where we commonly find hydrogen bonding. The first one is if hydrogen is bonded to fluorine. Fluorine is a very electronegative element, the most electronegative element. So the electrons are pulled very strongly to the fluorine, producing a very powerful permanent dipole. So the hydrogen becomes positive, the fluorine into the molecule becomes negative. This also happens when hydrogen is bonded to nitrogen, also a fairly electronegative element. So for example, in something like ammonia, the nitrogen is pulling the electrons from the three hydrogens. The ammonia or the nitrogen end of the molecule becomes negative, the hydrogen end becomes positive. And then our third case is if hydrogen is bonded to oxygen. So something like a water molecule, oxygen of course is much more electronegative than hydrogen, so electrons are pulled toward the oxygen and away from the hydrogen, and that makes the oxygen end of the molecule negative and the hydrogen end of the molecule positive. So what should we know in the end about intermolecular forces? First of all, intermolecular forces are produced by the unequal distribution of electrons. Whenever the electrons are pulled to one side of the molecule or the other, we get intermolecular forces, and that happens in both polar and nonpolar molecules. Nonpolar molecules share electrons equally. So they're normally nonpolar, but they can temporarily become polar. As the electrons move around, they can move to one side, form these temporary dipoles. And the forces of attraction in nonpolar molecules are commonly referred to as London forces. In a polar molecule, the electrons are always shared unequally because the atoms have different electronegativities. So these molecules have a permanent dipole, and as we said earlier, their forces of attraction are known as dipole forces, or sometimes they're referred to as dipole-dipole forces. The strength of a temporary dipole depends on how many electrons are in the molecule. So if molecules are nonpolar, the more electrons in the molecule, the stronger its intermolecular forces will be. For permanent dipole, for polar molecules, it's all about the electronegativity. The greater the difference in electronegativities of the elements, the more powerful that permanent dipole will be. And then we just talked about hydrogen bonding. Hydrogen bonding is a permanent dipole. It's just a very powerful permanent dipole, and it's observed whenever a molecule contains a fluorine bonded to a hydrogen or an oxygen, or a hydrogen to an oxygen, or a hydrogen to a nitrogen. And the whole molecule doesn't have to be hydrogen and nitrogen, for example, as long as an H bonded to an N is part of the molecule, or an H bonded to an O is part of the molecule. So let's wrap things up by working through a few practice problems. In these problems, what I want you to be able to do is to look at a molecule and determine whether the forces of attraction are temporary dipole, meaning it's a nonpolar molecule, permanent dipole, or hydrogen bonding. Both of those would occur in a polar molecule. So for our first example, let's take a look at formaldehyde. Now if we apply our rules, the first thing we'll notice is there are 3 elements in this molecule, which means it's automatically a polar molecule. So the question is it just a permanent dipole, or is it hydrogen bonding? Hydrogen bonding is a possibility because hydrogen and oxygen are both in this formula. The key thing is, are the 2 atoms bonded together? To figure that out, we need to sketch out the molecule. If we sketch out formaldehyde, we'll see that it is a nice trigonal planar molecule, but the hydrogen atoms are not bonded directly to the oxygen. The H's are bonded to the C instead. So if the H isn't directly bonded to O, it can't be hydrogen bonding. It's got to be permanent dipole. For our second example, let's look at phosphine, pH3. Now phosphine has only 2 elements, which means in this case it's all going to depend on the shape of the molecule. With 2 elements, it depends on the geometry. So once again, we'll need to sketch it out. If we do, you'll notice that pH3 is a trigonal pyramid. It's not trigonal planar because the phosphorus has a non-bonding pair of electrons. So this molecule is not symmetrical, which means it must be polar and thus has a permanent dipole. Octasulfur, again, if there's only 1 element, that makes it relatively simple because the rule was if there's only 1 element, it is going to be a non-polar molecule, which means it will have a temporary dipole. We don't really need to know what the shape of the molecule is if there's only 1 element, but sulfur is a rather interesting molecule. It's an octagon, sort of like a bent-up stop sign. And finally, difluoromethane. Now, difluoromethane has 3 elements, so we know it's going to be polar. The question is it hydrogen bonding or just regular permanent dipole? Once again, hydrogen bonding is a possibility because we have both hydrogen and fluorine. We need to sketch the molecule out to see whether the hydrogen and fluorine are attached to each other. If we do that, we see that the hydrogens and fluorines are not actually bonded to one another. All 4 of those atoms are bonded to the carbon. So it's not hydrogen bonding, it's just going to be a permanent dipole.